Okay, I'm just going to go ahead and get started, and if somebody comes later on in the evening, I can answer some questions then, but until then, we are going to be talking about section 8.3, which is Bayes' theorem, and yeah, so as I was reading through this, like when we were looking at like the definitions of like some like of different things within like the theorem and like the problems we were doing in the section. Number one, like my first thought was like tree diagrams are really, really useful here. And they did like mention it like several times, but I will say it again, like tree diagrams are going to be your friend for this section. Another thing, I'm going to go ahead and I'm going to write the equations that we use in this section down so that we can kind of keep track of what's going on with them. Let's do it over here. And so our equations are going to look something like this. Our first equation is we're going to say the probability of an event is equal to the probability of that event happening in A1 plus the probability of that event happening in A2, and so on and so forth. And so when I put a n here, I just mean any number. It's just going to keep going on and on and on. Okay, so this is referring to a probability of mutually exclusive event, like mutually exclusive sections. So the way that they like defined it is like this is sample space A1, this is sample space A2, and this is sample space A3. And in each of them, we can do event E, but basically like it's different event E's, sort of, because this is sample space A1 event E, A2 event E, and A3 event E. So they're all the same event, but you get to them through different routes. And a good way to visualize that is a tree diagram, of course, which is in your book on page, where did it go? I am looking in on page 445. They had the example with the urn. So basically, like the way that they kind of would like set it up is that you say, okay, so here's A1 and here's A2 and here's a bunch of events. This isn't E, this is E, this is F, and this is G, and this is E, and this is, I don't know, D and C. So you can get E from both of these from both of these pathways, but these don't have to be the same for each of the individual events. Anyway, and I think that the urn example on page 445 did a really good job of like outlining that, and saying that like one urn has two colors of balls in it. I don't know why they're urns. Seems kind of funny to me that they picked an urn, but yeah, so we have urn 1 that just has black and white balls, and then urn 2 which has yellow black balls and then a white ball. And then like what are the chances you get a black ball, like given that you pick an urn randomly? It does seem really weird that they're urns. Anyway, so the point is that this is kind of like setting up using the language that we know for solving those kind of problems. So yeah, when we were thinking about a sample space like that, we would have like A1 sample space and A2 sample space. Event E is in these, and the way that we define this is E intersecting with A, or A1, and E intersecting with A2, and so that's how we would find like probabilities and like actually calculate a probability through there. Okay, so this section, we start talking about a different kind of equation. which is very, very similar to this one, but it differs just a little bit. So we have the probability of event E happening is equal to the probability of A1 happening times the probability of event E given A1. Because remember from last week, this line here means given. Plus the probability of A2 times the probability of event E given A2. Okay. And I think again, a really good way to look at this is through its Triga diagram. Here we have A1, here we have A2. Here we have event E, here we have event E, and then I'm going to do the not E's in different colors. So this is just not E, and this is just not E. So the way basically that we do it, if we just were looking at a tree diagram and you asked me what the probability of E was going to be, and I didn't even know this equation, I would say, okay, so like where do I start? I say the probability of getting A1 is whatever the probability of A1 is. So let's say this is 0.5, so it's like a half a chance of picking A1 or A2. And then let's say this is another 0.5. So here I would have 1/2 times 1/2, 1/4 chance of picking E. And here I would also have 1/2, and this is 1/2. So basically you just multiply it through. And you get like your end result saying this is again 1/4. That is exactly what this equation is saying. In no uncertain terms, it starts with what is the probability of A1 happening. There's A1. Okay, so now that we're at A1, what is the probability of E happening given that A1 has like occurred? So like we look at here and we say there's a 1/2 chance after A1 has already occurred that we get E, and then there's a 1/2 chance we don't get E. So like what can we do with this? It's 1/2 times 1/2 here. And then again, it's 1/2 times 1/2 down here because it's the same process. What is the probability of getting A2? Given A2, what is the probability of getting E? So that equation, we have essentially used it before because we've solved things using this process before. It hasn't been explicitly stated, but don't worry, it's something that you guys have used before. Okay. Give me a sec. I'm gonna see. Oh, just a reminder too. This can continue as well. So this is just plus PAN times PE given AN. Again, this N just means any number, whatever, however high these things go. Okay. All right. Now we actually get to Bayes' theorem. So Bayes' theorem is we have a sample space that is partitioned into n events, and just as a reminder, partitioning means that all of the subsets of a sample space are not empty, and there is no intersection between any of them, and when they all are summed together, you get S. Okay, so Bayes' theorem, we have the probability, and that definition of the partition is just on page 449. So for Bayes' theorem, we have the probability of A sub J given E is equal to probability of A sub J times the probability of E given A sub J all over the probability of E. Okay. So things to know about this equation. J is just a number. It is a number. J is a number. Somewhere in, if we have 7 different like partitions in the sample space, J could be anywhere between 1 and 7 sort of thing. So J is just a plain old number, and you're never going to have like an actual like J there. It's not going to be something like that. Okay, so this continues to become a little bit more specific by bringing in what we have from up there. So the probability of A, given that E has occurred, or E, like it's the case, is the probability of A times the probability of E given A all over. And so now we know from up here it's going to be the probability of A1 times the probability of E given A1 plus the probability of A2 times the probability of E given A2, dot, 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 dot. So you just continue. For example, if there were 7 partitions, you do that 7 times. So you just want to find the total number of E. So yeah, so that is what Bayes' theorem is talking about. So what does this mean? We will do obviously several problems like analyzing like what this actually means, but basically this is saying, so we have this tree, right? And we know we have this end product. What we're asking is what is the chances we got to our end product from here versus here? Which path did we take? Because from here we don't get to see what path we took to the end product, because these end products look the same to us. If this is E, all we can tell is that we have event E. We don't know how we got there. So we're trying to figure out, did we go A2 to E, or did we go A1 to E? And that's what this is asking. Like, what is the probability we took the path of A1 getting to E? Okay, so I think that's probably enough, just like going over the equations. Let's actually try to do some problems. Okay, so let's start. We're gonna do problem 5 through 17 odd. And so this is on page 453. And I would remind you guys that it's highly encouraged that you guys just take a look at these problems before you continue on in the video. Just like go through, try to do the problems, see where you struggle, see if you can skip this part of the video because you guys know exactly what you're doing. Just like try to like evaluate where you are with the work. And okay, so this is your cue. I'm going to start solving these problems now. We have this tree diagram that is given to us. And I'm going to draw it right here. So we have these different A, B, and C. And then after that, there is either E or not E. So I'm going to just finish drawing all of this out. Oh, and then we have probabilities for all of these. So this is 0.4, 0.2. Oh, this is, I'm wrong. I better look at the book more closely. Okay, so this is 0.6, I put E on top and E not on bottom. The book has it reversed. So this is the same thing. You just have to make sure that your probabilities are correct. So this is 0.8 and this is 0.3. And then when it comes to E, this is 0.4. This is 0.2. This is 0.7. And these three, we have 0.1, 0.6, and 0.3. Okay. So we have a whole list of things to find given this set of information. We're going to start with problem 5, which is saying what is the probability of E given A. So the easiest way to do this is say, okay, so we have A. A is given. We're at this point. I always like to think of it as like a road that you're traveling on. So you've passed this fork. You're here now, and you're looking at this fork in the road. Are you going to go with E, or are you going to go with not E? And the chances, the probability that you go with E when you're at this point is going to be 0.4. You're at this point right there. And there's a 0.4 chance of you getting E. Okie dokies. So we're going to do that exact same thing for number 7 and number 9. Process is basically the same. We're going to say, okay, so we're at this point B. Where do we go from here? What are the chances we get E? Here, P of E given B is equal to 0.2. And here, P of E given C is going to be equal to 0.7. And we're just kind of doing the odd ones, especially so that you can like look in the back of the book and like check yourself. But as a side note, for example, 6 is the probability of E not given A, and it's literally the exact same thing. So we're at this point. What are the chances we don't get E? And that answer is going to be 0.6. So it's the same process. Okay, so let's try problem 11. Let me clean up this area a little bit. So problem 11 is asking us about the probability of E in total. As we discussed earlier, there are different ways to do this, but the easiest way, given the information that we have, is to say the probability of E in total. We're basically going to follow the path. We're going to start here, and we're going to say, okay, so if I go to A and then to E, my chances are I have a 0.3 chance of going to A, and I have a 0.4 chance of going to E. So this is the probability of A times the probability of E given A. It's the exact same equation that we were talking about earlier. And it's pretty intuitive once you like get used to it. Like get used to like the fact that it's like an equation. Like you guys have been doing this. Okay, so same thing here. We go B and we follow E, and so this is 0.6 times 0.2. Again, probability of B times probability of E given B, which is like something that we calculated up there. And then same thing. So this is 0.1. 7. Okay, so we're gonna have to put these all together. So I'm just gonna write it all out in one big old equation. And I'm writing this in terms of fractions just because for me it's easier to do in my head, but for sure you can, no, it's not easier for me to do it in terms of fractions. I'm just gonna feel free to use a calculator if you guys want to. Okay, so this is 0.3 times 0.4, so it's 0.12, it's like 3 times 4. Oh, shoot. Just got ink all over this. Okay, and so here we have 0.12 and plus 0.07. Okay, so we add all of these up. And that's 631. Okay. So that is the probability of getting E just in general. Okay. Nice. So we have got 11 done. Now let's look at 13. So this was the probability of A given E. So this is when we start talking about Bayes' theorem. What we know here is that we are at E. So we are at one of these three places. We don't know which one because we don't know how we got here. We're asking ourselves, what is the chance, probability of A given E? What is the chance we got to point E via this path, point A? And in order to do that, we're going to be finding all of this. Okay, so we're going to be using Bayes' theorem. So this is equal to the probability of A times the probability of E given A all over the probability of E happening. So we know all of this from the tree diagram and from problems that we've already done. The probability of A is equal to 0.3. That's right here. The probability of E given A is up here. Circle it. And the probability of E is right here. So this is going to be it's basically going to turn out to be 12 over 31 because I can multiply each of these by 100. So anyway, so our answer for number 13 is 12 out of 31. So I'm going to rewrite that up here. So that's P of A given E is equal to 12 out of 31. Okay. So now let's do number 15, which is the probability of C given E. So it's the exact same process we just went through, except we're doing it with C instead of with A. So we have 15. We're looking for the probability of C given E. So this is going to equal, as we decided with our previous equation, the probability of C times the probability of E given C all over the probability of E. So this is going to turn out to probability of C is going to be 0.1 times the probability of E given C, which is 0.7, all over 0.31. So this is 7 over 31. Okay. Now let's look at 17, which is the probability of B given E. So we're just doing the exact same thing with B. This is going to be, I'm going to write out the whole equation just so that, for the sake of clarity. This is equal to 0.6 times 0.2 over 0.31. This is 12 out of 31. Okay. So, yeah, basically, like you'll notice that this chunk is very similar to how we went about finding this. It's the same as how we went about finding the actual probability of E. Why are those equations also similar? And how did we get different answers based upon all of these things? Okay, so I'm gonna rewrite this table, and then we are going to, I'm just gonna clear some of this. We're still on page 453. And we're still gonna use this because we're still kind of talking about okay. So when we're calculating this, we have 0.3 times, sorry, I gotta look back at the table. This is 0.4. And this is 0.6, 0.1, 0.7, 0.3, 0.8. I mixed them up again. Okay. So this is 0.2 and 0.8. So when we're trying to find the entire probability of E, we're following these paths. We're saying probability of getting to A, going to A, and then going to E is 0.3 times 0.4. And so this is 0.12 overall. And we do the same thing for B and for C. And we ended up with 0.12 and 0.07 here. Then, to find the probability of E, we added all of these together to get 0.31, or the chances we get E regardless of not counting what paths we took. We don't care how we get to E, we just want to know if we got to E. Okay, so the way that the reason that Bayes' principle is basically working is that we're just taking the probability of getting E. So consider we know we got E, which is basically what Bayes is saying. We have the probability of A given that E has happened. So the probability, we go A, E is 0.12. And the probability we get E is 0.31. So there is a 12 out of 31 chance that if we are at E, we got there via path A. There's also a 12 out of 31 chance that if we are at E, we got there via path B. there's only a 7 out of 31 chance that if we're at E, we got there via path C. So Bayes' theorem is basically talking about how did we get to where we are? Like what were the previous things that enacted upon that? And this is basically just taking like a probability, but it's like considering other probabilities. So like if this is just us getting E, and this is how we got there. So Bayes' theorem actually makes a lot of sense when you think about it in terms of like how to solve the problem. Okay. It was a kind of long example. We are going to do problem 27 next, which is given to us via these tables, or this one table. And I think first thing we should do is make a tree diagram. So we're doing 27, and this is on page 454. So we're going to start with what jar. So we have jar 3, jar 2, and jar 1. And then from there, we have a red ball. And for jar 1, there are 5 out of 11. So I'm actually just going to write this as a fraction, not as a percent. So there's a 5 out of 11 chance we get a red ball for jar 1. For jar 2, that's not 11, that's 16. I screwed up. Can't do addition, I guess. Okay, so 5 out of 16. Here it is 3 out of 16. And how did I lose a line in jar 3? Okay, this is a 3. This would be 7 out of 16. Okay. Then there are white balls, which I'm just going to use blue for because I really don't have, oh, we can't do white on this. And this is 6 out of 16, 4 out of 16, 6 out of 16, and 5 out of 16. And then black. And this is, sorry, this tree diagram got pretty crimped. For, oh, it's blue, not black. Ugh, okay. I'm just gonna decrimp this, redo it really fast. Give me a sec. Okay, we're back. This is much cleaner. Okay, so we have this graph of like what's all in the different jars. We figured out the probability. For instance, if we pull a random ball out of jar 1, what is the probability that that jar is red? Well, the probability is the number of red balls divided by the total number of balls. In this case, it's 5 over 16. So that's what we have in terms of probabilities. We could find decimals if we wanted to, but we don't really want to do that right now. And we aren't given probabilities for the jars because the jars are going to be chosen at random. So basically what that means is that it's just a 1/3 chance for all of them. So given all of this information, we have a lot of different questions to answer. Starting with what is the probability that the ball is red? So the probability of a red ball is going to be the probability of getting a red ball via jar 1. So that is the probability jar 1 times the probability of getting a red ball via jar 1. So it's red via 1 plus the probability of 2 red given 2 plus the probability of 3 times the probability of red, given 3. Okay, so we're going to have to fill this all out. The easy way of thinking about this, though, is saying, okay, so we are at 1/3 times 5/16, which is this times this. And then we're going to move down here and we're going to say 1/3. Sorry, I like to color code things, if you can tell, just to like help you guys keep track when you're watching the video, because sometimes my handwriting can get a little like wonky, or I'll like, as I'm talking, I'll like skip over things that I'm like thinking. So I want to like try to make it as clear as possible for you guys what is going on in my head. So that's why I'm spending all this time with the color change. Just an FYI. So this is 1/3 times 3/16 plus, and then over here we have 1/3 times 7/16, because we're still talking about red balls. And so again, all of these 3 results are going to get us a red ball. So this is all going to simplify down into 5/48 plus 3/48 plus 7/48, which is equal to 15/48. And what we can do is we can multiply each of these sides by 1/3. And we're going to get 5/16. So this is just simplifying this fraction. So yeah, the probability of getting a red ball, in general, regardless of how we get it, is going to be 5/16. Okay, so we've got all of that. Give me a sec to erase. Next, we're going to be looking at the probability of white ball. So this is your like opportunity to just like get ahead and start thinking about how to do that. It is the exact same process that we just went through. We are going to start. I'm not going to write the whole equation out. Basically, what we're doing is 1/3 times the probability of white. So the probability of white is going to be 1/3 times 6/16 plus 1/3 times 1/4. That's 4/16. Plus, and I just simplified it down, 1/3 over 5/16. 1/3 times 5/16, 6/48 plus 5/48 plus 1/12, which is 4/48. So it's going to turn into 6/48 plus 5/48 plus 4/48 is equal to 15/48, which we just figured out is equal to 5/16. So to get a white ball, it's again 5/16. So I'm going to start writing these in the corner over here so we don't forget. And then we just figured out that the probability of white is equal to 5/16 as well. Okay. Let's, for part C, do the same thing for a blue ball. Give me a sec to do some erasing. Okie dokies. So same process, basically. It's going to be 1/3 times 5/16 plus, I'll write this down, 1/3 times 9/16 plus 1/3 times 1/4, 4/16. Depending on what's easier, because we're going to need to simplify this, basically is like my thought process, but We're going to get 5 over 48 plus 9 over 48 plus 4 over 48. And so this is going to be 18 over 48, or 6 over 16. And this can be further simplified into 3 over 8. So the probability of blue is going to be equal to 3 over 8. Okay. So that's where we're at right now. We've got parts A through C down. This is kind of material from like weeks previous. Now we're going to be looking at stuff involving Bayes' theorem. So part D. What are we looking for here? Well, we are looking for, if the ball is red, what is the probability it came from jar 1? So we are looking for the probability of jar 1 given that the ball is red, right? So we know this is equal to the probability of jar 1 times the probability of red given jar 1. This we know, this we've figured out, and divided by the probability of red. So let's put it all together. The probability of 1 given red is equal to the probability of getting jar 1 is 1 over 3. The probability of getting red given jar 1 is 5 over 16. The probability of getting red is also 5 over 16. So we can like multiply this all out to simplify it. This is 5 over 48 divided by 5 over 16. If you remember, this is basic like fractions. Basically, the way that you do this is by just in terms of like solving. You can of course use a calculator if you feel more comfortable with doing that. Sometimes I feel weak on manipulating fractions too, so it's fine. But basically what you're gonna end up with is 5 times 16 divided by 5 times 48. These 5s are going to cancel, and of course 16 divided by 48 is equal to 1 over 3. So given that we have a red ball, we have a 1 over 3, we have a 1/3 chance that it came from jar 1. That kind of makes sense. Okay. So let's try the next one. If the ball is blue, what is the probability it came from jar 2? So probability of jar 2 given blue. I'm going to use the same thing, probability of 2 times probability of blue given 2 over probability of blue. So okay. So I would simplify starting here. I would say I'm going to get rid of that and make that a 3. And I'm going to get rid of that and make that a 6. So we're going to end up with 3 over 6, which is equal to 1/2. All right. So the probability that if we have a blue ball that it came from jar 2 is 1/2. Okay. So our last piece of this problem is going to be if the ball is white, how do we know if it came from jar 3? Set it up in the exact same way. We want probability of 3 given a white ball. that is equal to the probability of getting jar 3 times the probability of a white ball, given that we got it, we pulled a ball from jar 3, which is 5/16, all divided by the probability of getting a white ball, which is also 5/16. Something else you can do is just cancel this out right now, because this is like one term. Manipulating fractions is actually the worst, in my opinion, and I still second guess myself every time I like try to multiply fractions, so like don't worry. If like I swear, like use a calculator on your homework and stuff if it makes you more comfortable. So yeah, so basically this is going to be 1/3. So cool, that was problem 27. And I think we're gonna wrap this up with one more problem. Give me one sec, and I'm gonna pick one out really fast. I have a bunch on my list, and I want to pick the best one. Okay, so there's a one that looks really cool, number 51, that is testing for HIV. But we're gonna be, that would have us dealing with some pretty like big weird numbers. So I think we're just gonna do number 29 instead, which is talking about color blindness. So yeah. Okay. So problem 29, this is page 454. According to the 2000 US Census, 50.9% of the US population is female. NBC News reported that 1 out of 12 males, but only 1 out of 250 females is colorblind. Given that person randomly chosen from the US population is colorblind, what is the probability that they are a male? Okay, what are they asking for here? So they're asking for given, oh, something is given. So we're going to be looking at probability of given. So we're looking for the probability of male given color blindness. So what is the chances if we have a random colorblind person that they're going to be a dude? Logically speaking, this number is going to be pretty high. So we're expecting something pretty high because a lot more guys are colorblind than girls are. Okay, so where are we going to start? I would start with making a tree diagram. What a surprise. Okay, so we have, this is 50.9%. In terms of fractions, that is 509 out of 1,000, which is a pain to work with, but honestly, when I was sketching out this problem, I just did 1/2 and 1/2, but I think we should like go all the way right now. So this would be 491 over 1,000. So this is being female and this is being male. Okay. Then from here, we have a 1 in 250 chance for being colorblind. And then I'm just going to call this not. So this is 499 out of 250. And here it is 1 out of 12 to be colorblind, and 11 out of 12 to not. Okay, so we're basically going to use this to find what we need. We know that this is going to be equal to the probability of being male times the probability of being colorblind, given that you are male. So this is all just stuff from our equation, divided by the probability of being colorblind. So the probability of being colorblind is the first place that we're going to start, just because it's the biggest chunk of things to do. So that's going to be this. Probability of being colorblind is going to be equal to the chances, like if the chances you are female and colorblind plus the chances you are male and colorblind. So that's 509 out of 1,000 times 250 plus 491 out of 1,000 times 1. Okay, so this is going to be, you know what, I'm gonna pull out a calculator so I can just give you a decimal here, so we don't have to do the messy fraction thing. Okay, so I did all the calculator stuff, and I got there is a approximately 6% chance that a person is colorblind. Like we're like not thinking about gender here, like if it's just a person that they're colorblind. So that is this up here. So I'm going to set this up. This is going to be 0.0613. Okay, what is the probability that somebody is male? Well, we're just going to go with a half. So, oh wait, we're not going with a half. We're going with, we are going with 0.491 because we said that this was 50.9% or 509 out of 1,000 or 0.509. So to get the opposite of that, we just subtract this from 1. So this is 1 minus 509 is equal to the 4.491. So this is the chance of being a male times the chance of being colorblind given that one is male. So that's where we cut it off here. We say we know that we're at the male point. What we need to know is what is the chances of being colorblind, and the chances of being colorblind are 1 out of 12. And that is 0.0833. So we're just going to multiply all of this out. Okay, so the answer I got didn't quite match with what was in the book. This happened last week too, and it turns out I was wrong. So I'm going to punch it into the calculator one more time just to be sure. Okay, so this is not quite right. This would say that the answer is 66.7%, which is not what the book says. The book tells me that my answer is actually 95.7%. So I screwed up somewhere in here. That's okay. We're going to figure out where I screwed up. Let's just walk through this one more time. So we're trying to find, let's start all the way at the beginning. We are looking for the probability that somebody is male, given that they are colorblind, which is equal to the probability of being male times the probability of being colorblind, given that one is male, divided by the probability of being colorblind. So I am going to erase, actually I'm not, I want to keep that up there to compare and contrast. I'm very confident that given the information that we have, that this is the probability of being male, because it's 0. Yeah, it's 50.9% is female, so this is the probability of being male. So I'm good with that, times the probability of being colorblind, given that one is male, which is 1 out of 12. And 1 out of 12 is indeed, so this part should be right. Okay. Okay, so I think I know where I screwed up. This doesn't look right to me. Right there. It looks like too big a number. So I'm going to just go ahead and type this out again. It looks like I missed a 0 somewhere. You know, missed a 0. Okay, so this is actually 0.00204. So I missed a 0 here, and as such, this whole thing was off. So that's not right. What the actual answer is, the probability of being colorblind, is actually going to be so it's actually going to be 0.4, no, that's a lie, 0.0429. Okay, so I'm going to put that up here. And there's a big difference between this. So I'm just going to go ahead and type all of this out again. Okay, and what do you know? Now I end up with 0.954, which is pretty darn close to this answer that the book has. Why it's not precisely the same, I'm not sure. But it's probably a rounding error. They probably calculate it using more numbers after this. This is actually like 3.6 or something. Doesn't really matter. It's a rounding error somewhere. This is a 95.4% chance. Again, what does this mean? This means that if I pick a random colorblind person, there's a 95.4% chance that that person is male. And that's the problem. This was also a good example of going through and figuring out where something went wrong. Kind of looking over the work that you've done. It happens to everyone. Don't panic if it happens to you. But it's something to look out for. If something is supposed to be very, very small, make sure it's very, very small. So yeah. Thank you guys for watching. I think I'm just going to wrap this up for tonight. Yeah, you guys have a wonderful night, and I hope you guys have a good weekend. See ya.